This is the third lecture of week 8. So let's consider a case where the effect of class size varies by the percentage of English learners. We may think that the effect of reducing student-to-teacher ratio may be greater for the districts that have a high percentage of English learners because they tend to benefit, maybe they benefit more from having a smaller student-to-teacher ratio. In this case, what we're saying is that change in test score over change in student-teacher ratio depends on percentage of English learners. So we are going to look at 3 different ways to model this. The first is looking at the interactions between 2 binary variables. The second is looking at the interaction between binary and continuous variable. And the last, we're going to examine interactions between 2 continuous variables. So let's first start off looking at the interactions between 2 binary variables. We're going to start with the multiple linear regression model with 2 dummy variables, D1 and D2, where the values equal either 1 or 0. In this case, beta 1 is the effect of D1 on Y, holding D2 constant. So in this case, beta 1 is constant no matter what the D2 value is. Let's say that we want to model the case where the effect of D1 actually varies by D2. So in that case, we want to include an interaction term, which is D1 times D2 as a regressor in the model. So let's look at the effect of D on Y, D1 on Y with the new model. In order to measure that, we're going to look at when D1 is equal to 0. Then you plug in D1 equal to 0 in the appropriate place, and what you get is beta 0 plus beta 2 D2. And then we're going to look at when D1 is equal to 1, and you have this function. When you subtract B from A, beta 0 and beta 2 D2 cancels out, and what you have left is beta 1 plus beta 3 D2. This shows that when D1 changes the value from 0 to 1, that effect of D1 on Y depends on this term beta 3 D2. So it depends on the value of D2. Let's go through our example. So here we have this new variable called high STR, where if STR or student to teacher ratio is greater than or equal to 20, then it equals 1 or 0 otherwise. And then we also have a new variable called high English learner, which says that if percentage of English learner is greater than or equal to 10%, then it's 1 or 0 otherwise. So these are 2 dummy variables that indicates whether you have a high student to teacher ratio or high English learners in the district, or high percentage of English learner in the district. So when you run a regression of test score on these 2 dummy variables and the interaction term, we get these coefficients. Say you want to measure the effect of having a high student to teacher ratio when high English learner is equal to 0. So in this case, we plug in 0 for the high English learner. And what you have left is negative 1.9. So whenever high student to teacher ratio is equal to 1, then the effect of high student to teacher ratio on test score is negative 1.9. Say now you want to know what is the effect of high student to teacher ratio when high English learner is equal to 1. So now you plug in 1 instead of 0 in the appropriate places. And what you have left is that the effect of having high student to teacher ratio is negative 1.9 minus negative 3.5, because this term becomes negative 3.5 times 1 times 1. So what this shows is that the effect of class size on test score is larger when you have a high percentage of English learners. However, when you look at the t-statistics for the interaction term, by dividing the coefficient by the standard error, you see that the interaction term is actually not statistically significant. Instead of estimating the effect of high student-to-teacher ratio, what if we want to know the actual test score under different cases? So say we want to know what is the average test score when you have a low percentage of English learner and low student-to-teacher ratio. This means that high EL is equal to 0 and high STR is also equal to 0. So if you plug this in, what you have remaining would be 664.1. We can do that for all the other values too. So say you want to know what is the average test score of having a low percentage of English learner but high student-to-teacher ratio, then in this case, you plug in high STR equal to 1 instead. So in this case, because you're plugging in high EL is equal to 0, these terms cancel out, and what you have left is 664.1 minus 1.9, which equals 662.2. And you can do this for all the other values by plugging in different values for high EL and high STR to get the average test score. Let's look at the second case of interactions between continuous and binary variable. So in this model, we start off with one continuous variable x and a binary variable or dummy variable d. So in this case, if you want to look at beta 1 is the effect of x on y holding di constant. So this beta 1 or the effect of x on y doesn't depend on d. If you want to have the effect of x depend on d, then we can include an interaction term, which is d times x as a regressor. So one of the advantages of this regression model is that it allows you to have two distinct regression lines depending on the dummy value of the dummy. So for instance, if dummy variable is equal to 0, then we can plug in d is equal to 0 and get one regression line, whereas if the dummy is equal to 1, then you get another regression line. Let's think of an example of trying to estimate the effect of education on earnings. So in this case, earnings is the dependent variable and education is a continuous variable. And let's say we have a dummy variable called male, which equals 1 if it's male and 0 if it's a female. In this case, when you have this dummy variable male equal to 0, we get one regression line, which measures the effect of education on earnings for only females. When you plug in the dummy variable male is equal to 1, then you have another regression line, which effectively measures the effect of education on earnings for only males. So this model allows you to have different effects of education on earnings for male versus female. So including the interaction term between binary and continuous variable allows you flexibility in the regression model. So using the previous case, say we were interested in the relationship between earnings and education. But we also think that the relationship between earnings and education differs based on gender. So in that case, we can model this in several different ways. We may think that, for instance, given no education, maybe the male makes higher wage than female. But then after a while, the slope is constant, meaning that as the number of education increases, the earnings for male versus female may increase at the same rate. We can also think of another situation where you start off at different wages with no education, but then the slope also differs between two groups. So we may think that for male, the return to education is higher, so it's steeper than female, whose return to education is lower, so they have a flatter slope. We can think of a third case where for males and females, they start off at the same place, so your earnings are the same when you don't have any education. But then the slope is actually different. So maybe male has a higher return to education, so their payoff for earning greater number of years of education is greater than females whose slope is lower. So we can model this more flexibly with inclusion of the interaction term. So how do we interpret the coefficients? We're going to follow the same steps as before and start off with the basic regression model and then see what happens when you change x by a small amount. This will cause y to change by a certain amount, and then subtract db from a, and we get this change in y equal to beta 1 change in x plus beta 3 d change in x, and then once you rearrange it, we get this function change in y over change in x is equal to beta 1 plus beta 3 times d. This shows that the effect of x on y is not constant. It has another term that depends on d. So in our previous example, the effect of education on earning is not constant for both male or female. It actually varies depending on whether you're female or male. So let's look at another example. Here we're regressing test score on student to teacher ratio, which is a continuous variable, and high English learner, which is a dummy variable, and the interaction between these two terms. So when the dummy variable, high English learner, is equal to 0, we can plug that into the equation and we get one regression line. When high English learner dummy variable is equal to 1, we can plug in 1 instead of 0 and we get another regression line. So basically you have one regression line that measures the effect of student to teacher ratio on test score for the districts that have lower percentage of English learner, and you have another regression line that measures the effect of STR on test score for the districts that have high percentage of English learner. We can also see that the coefficient for STR is larger for when high English learner is equal to 1 versus when high English learner is equal to 0, which shows that the effect of student to teacher ratio or the class size has a bigger impact on test score when there's a higher percentage of English learner than low percentage of English learners. So let's talk about testing 3 different hypotheses. The first hypothesis that we want to test is that both school districts, regardless of whether they have a high percentage of English learner or low percentage of English learner, have the same effect of student to teacher ratio on test score. So in order to test this, we need to test if the coefficient on the interaction term is equal to 0. So if the interaction term is equal to 0, then both, regardless of school district percentage of English learners, the effect of STR will be constant for both school districts. When you do the t-statistics, you get the result that we don't reject the null of the interaction term being 0. So it seems to indicate that regardless of the percentage of English learners in school district, the effect of student to teacher ratio on test score is constant. The second hypothesis that we want to test is that they have the same intercept. So meaning that the test score is actually the same for high percentage English learner district and low percentage English learner district. And the way to test this is testing if high EL variable or coefficient is equal to 0. So if high EL is equal to 0, then you'll have both of these terms disappear and you'll have both of the school districts average test score will be 682.2. When you calculate the test statistics, we also get the result that we don't reject the null that says high EL is equal to 0, indicating that both districts, whether it has high percentage of English learner or low percentage of English learner, starts off at has the same average test score. The last hypothesis that we want to test is that the regression line is the same regardless of whether you're in the high English learner district or low English learner district. So in order for you to test this, you can do an F-test where the high English learner variable is equal to 0 and the population coefficient for STR, the interaction term, STR times high EL is equal to 0. And when you calculate the F statistics, it shows that we actually do need to reject the null, meaning that the coefficient concluding that at least one of the coefficients, whether it's high EL or the interaction term, at least one of them is not equal to 0. But this is contradictory to what we have tested before. When we have tested these coefficients individually, it shows that these coefficients are equal to 0. But when you test them together, it's giving us the conclusion that they are actually, at least one of them is significant, so they're contradictory. The reason why we're getting different results when you test them individually versus jointly is because of the high correlation between high EL and this interaction term. Because these two terms are highly correlated because one is basically a multiplication of the other, there's a high multicollinearity, and this inflates the standard error of the individual coefficients, making the individual hypothesis testing unreliable. So we can say that there is a strong evidence against the fact that both of these coefficients, high EL and the interaction terms, are equal to 0, and there is a high probability that at least one of them is statistically significant. We're going to talk about the third case where we're looking at the interactions between two continuous variables. So we start off with the multiple linear regression where we have two continuous variables, x1 and x2. It's the way it's written, the effect of x1 on y doesn't change depending on x2. But there may be cases where we think that the effect of x1 on y actually depends on x2. So in that case, we want to include an interaction term x1 times x2 in the model. So how to interpret the coefficients? We're going to follow the same steps as before and see what happens if x changes by a small amount, and subtract one from the other function to get that the effect of x1 on y is beta 1 plus beta 3 times x2. So this shows that the effect of x1 on y is not constant, but rather depends on the value of x2. So let's look at our previous example. So here now we have the student to teacher ratio and percentage of English learners in district as both continuous variables. In this regression model, we have an interaction term that allows the effect of student-to-teacher ratio on test score to change depending on the percentage of English learner. So previously, without the interaction term, we knew that regardless of the percentage of English learner in your district, when you increase student-to-teacher ratio by 1, your test score would decrease by negative 1.12. But with the new model, including the interaction term, when you increase the student-to-teacher ratio by 1, your test score actually would decrease, but it depends on the percentage of English learners. So you can see that with the numerical example. When you have a percentage of English learner equal to 0, then increasing the student-teacher ratio by 1 would decrease the test score by 1.12. But when you have the percentage of English learner in the district at 20%, then now your test score actually decreases by smaller amount. So including this interaction term allows you to have differing effects of student-to-teacher ratio on test score depending on the percentage of English learner in the district. So here we're going to test 3 different hypotheses. The first is that we are going to see if the interaction term is equal to 0. Looking at the coefficient and doing a t-test, we get the result that we cannot reject the null at 5%, meaning that the interaction term coefficient is not statistically significant. Next, we want to test if the coefficient for STR is equal to 0. So in this case, our t-test says that we cannot reject the null at 5%, meaning that the coefficient for STR is not statistically significant. The third hypothesis that we want to test is that both the STR and the interaction term is equal to 0. With the F-test, we actually get the result that we can reject the null at 5%, meaning that at least one of these coefficients is not equal to 0. So again, we get a contradictory result when we do a joint hypothesis testing versus when we test the coefficient individually. And same as before, this is because of high multicollinearity between the STR and the interaction term.